Okay, so it's my great pleasure to introduce Helmut Pottmann. I know Helmut for many years. We collaborated, we even talked and collaborated and talked many years, for many years. And he is doing work that is related to CGD, but in recent years, he's kind of switched to looking use of geometry in architecture. In fact, you founded the conference, AA, whatever it's called, AAW, of collaboration of geometry, making complex geometry using freeform surfaces, and started your company, I think, in that direction also. So in all, is very well known. He did lots of work in CGD in general, and as I said, in recent years toward architecture. And Helmut, thank you for joining us today, and you have the podium.
Thank you, Sean. Thank you for inviting me over. And thanks to all of you for listening to this talk. I see a pretty large number of participants, some good friends of mine among them. So I will talk about quad mesh-based mappings between surfaces, which is new in a sense, since most people use triangle meshes. And we found out that the use of quad meshes has some advantages. And this is what I'm going to talk about today. So I will first say a little bit on mappings between surfaces from an elementary geometric point of view, then turn to the quad mesh case, and then say a little more about discrete developable surfaces. And finally, we will look at applications in architecture, at structures made from planar quads, and at so-called asymptotic grid shales. So let's start with some basic math. We have a parametric surface parameterized over some UV parameter plane, and we take some domain D in this parameter plane and map it with a mapping X into, say, 3D. And then we have a point here, U0, V0 is mapped to X at U0, V0. Then the straight lines parallel to the U and V axis in the parameter domain, like these two here, are mapped onto the so-called isoparameter lines on the surface, and their tangent vectors are, of course, the partial derivatives of this representation X with respect to U and V. And these two vectors span the tangent plane at the surface point. Now, if we have a curve on a surface, we have to take a curve in the parameter domain, which may be parameterized over some interval I, and so we take a point T in this interval, map it first to parameter plane, and then into 3D. Mapping this interval into 3D yields a curve whose derivative C dot, so a tangent vector, of course, is by the chain rule a linear combination of the partial derivatives xu and xv. The coefficients here are u dot, v dot, which of course is a representation of the tangent vector of this curve in the parameter domain. Dots indicate derivatives with respect to t. Now let's consider a mapping between two surfaces, and for our analysis now it is sufficient to assume that the surfaces this map is set up with help of equal parameter values. So locally with some reparameterization you can always achieve this case. So if we have a point uv in the parameter domain, we have a corresponding point on the first surface, another point on the second surface, and this is the map between the two surfaces. From what I have said before, we immediately get the derivative map. So we have a point on one surface, a point on the other surface, the corresponding tangent vector spaces or tangent planes, if you like. XU is mapped to X bar U, XV to X bar V, and the general tangent vector U dot X V dot XV here corresponds to U dot X bar U plus V dot X bar V. So this is a linear map, geometric terms, if you like. It is an affine map between the two tangent planes. Now we take in the first tangent plane vectors of the same length, which means we take here a circle centered at the contact point. We map it with this linear map, and this circle, of course, is mapped in general to an ellipse, which has a major axis and a minor axis, and these directions, of course, are orthogonal and indicate the extremal length distortions of this mapping. Important cases are those where this ellipse C bar is actually a circle, which means that we have the same length distortion in all directions per point. This is a so-called conformal map. We could also say that this derivative map is not just an affine map, it is a similarity, which means composed of a rotation and a uniform scaling. Per surface point, we have the same length distortion in all directions, but this is a point-specific value and changing over the surface. Such maps, of course, preserve the angles. Similarities preserve angles, which you see here. We have this UV plane on the right-hand side, and here's a 3D model, and this orthogonal grid of straight lines in the UV plane is mapped onto this orthogonal curve network on the surface. There is a lot of work in computer graphics on conformal mappings. They are used, among other things, for example, for texture mapping. Let us now consider an even more special case, namely an isometric map, where this derivative map is a congruence transformation, a rigid body motion, which means such a map preserves lengths and angles of curves. So this is a deformation of some surface by pure bending where there is no stretching. There is a lot of work on isometric maps, for example, in geometry processing. An example is in connection with character animation or articulation of human poses and so on. Or there is some work, of course, in fabrication, which we will address a little later on. From a geometric point of view, it is important to note that isometric maps preserve the Gaussian curvature, which is the product of principal curvatures, and also the geodesic curvature of surface curves. And of course, as a special case, geodesics, namely shortest paths, are mapped to geodesics, which is clear anyway by the length preservation of isometries. So I've brought here up an example. We take a spherical patch here. The isoparameter lines are these meridians and the parallel circles. So this, in one direction, we have here geodesics. In the other direction, we have circles on a sphere, which have, of course, a constant geodesic curvature. And the sphere has constant Gaussian curvature. If we now perform isometric deformations of such a patch, shown here on the right, we can say these are all representing surfaces of constant Gaussian curvature. One family of curves, those ones here, are geodesic, shortest paths, and the other one have constant geodesic curvature. So now, after this short mathematical introduction, I'm coming to the computation of surface-to-surface maps via quad meshes. And let me just bring up here some use of quad meshes in various applications. They are preferred for character animation, for example. They are, of course, central in computer-aided geometric design. For example, they occur as control meshes of freeform shapes. In architecture, they occur in the panel layout and in the support structure. The inspiration of this work is actually quite unusual. It came from the logos of the Olympic Games in Tokyo, which actually couldn't be held eventually. If you look at this logo, it is a kind of checkerboard pattern of rectangles. In this case, only 3 types of rectangles. There are squares, rectangles of length to width ratio 2:1 and 4:1. And then there was this research scientist, Jihan Peng, working in the group of Peter Wonka, who wanted to generalize this. And he generalized this into 2D, making such patterns. And then, the question came up, can we do such things in 3D? And this actually was the starting point of the work I'm talking about today. The main results I talk about, you will find in this paper, which we had last year at SIGGRAPH. So we take a single quadrilateral for the moment. This is this black quad here, and consider the edge midpoints. It's very well known that they form a parallelogram. And why is this the case? Well, because of the intercept theorems. Look at this triangle here. This is a diagonal in the quad, right? And this is a connection of 8 midpoints, so they must be parallel. And this connection has half the length of the diagonal. So we really see that these edge midpoints form a parallelogram whose edges are parallel to the diagonals of the quad and of half their length. Now, if we apply this to a quad mesh, we get a checkerboard pattern of parallelograms. In particular, if we want a checkerboard pattern of rectangles, we need to make sure that in the original quad mesh, in each face, the diagonals are orthogonal. Now, let me point out actually that several meshes here play a role. The yellow mesh, which is shown here, is the quad mesh I'm talking about, then which we call the control. Then we have by mid-edge subdivision the resulting checkerboard pattern of parallelograms, and we have two diagonal meshes. So recall that in each face, the edges of these parallelograms are parallel to a diagonal in a quad face, and the diagonals in these quad faces can be arranged into two quad meshes shown here in red and blue, and I will call them the diagonal meshes. As a remark, if you have a checkerboard pattern, then there are infinitely many control meshes. Not all of them are beautiful. So most of them are nasty. We are, of course, after the nice ones in general. Now, in order to get some geometric understanding, we do the following. We have in 3D a quad mesh, the control mesh, the associated checkerboard pattern, and if you like, the diagonal meshes. And we view this as an image of something very simple in the plane, namely a regular grid. So we do in the plane, we have this yellow mesh, which is just a regular square grid. And we consider the diagonal meshes, and we put the U and the V axis into the diagonal direction. This sets up a discrete map from the plane into 3D. A face here in the plane corresponds to a quad face in 3D. A square in the plane corresponds to a parallelogram in 3D. And this map from the square in 2D to the parallelogram in 3D is actually a discretization of this linear map, which I have been talking about before. So we have in these, I call them black faces, also they are dark blue here. Between these corresponding faces, we have these derivative maps. You could also say the following: if we pick a face in this control mesh, in this quad mesh, then the diagonal vectors, this and the other one, are actually can be seen as the partial derivative vectors with respect to u and v. More precisely, if we take a smooth mapping from the UV plane into 3D, and we evaluate this smooth mapping at the midpoints of the faces in 2D, so MF is such a face midpoint, we can get the following Taylor expansion, namely the partial derivative with respect to U at the face midpoint is actually this difference vector here, vi2 minus vi0, divided by the edge length here. So here the edge length of the grid is h, so the diagonal length is square root of 2 times h. So we get this Taylor expansion, and this says something because it has an accuracy of order 2 and not just 1. So the error term is not O of h, it is O of h squared. And of course, the same applies in the other parameter direction. Now we can easily do quad mesh deformations with help of these checkerboard patterns or with help of this discretization, which I've just mentioned. The goal is to deform a mesh M, let's say, into a mesh M prime under certain constraints. It could be a conformal map, an isometric map, or so. And of course, we have to look at the corresponding faces, corresponding diagonals, and their angles. So let me start by making this more detailed. For discrete conformal maps with help of these checkerboard patterns, we have to make sure that corresponding parallelograms are similar to each other, which means that diagonals in corresponding quads of M and M prime possess the same angle and length ratio, which is very easily expressed here in this condition. So this is this factor, the scaling factor for the squared length. So this is totally simple. The last equation involving this inner product, of course, makes sure that the angles are the same because we already have these first two equations. So this inner product relation is enough. So it's extremely simple constraints, quadratic essentially. Now here we can go to the special case of an isometric map, which means that these factors lambda f from before are equal to 1, corresponding parallelograms, mid-edge parallelograms are congruent to each other, and these are the constraints, quadratic constraints. So really super simple. This can be easily cast into an optimization algorithm. We use a nonlinear least squares formulation, which is solved with the Levenberg-Markert method. The objective function to achieve an isometric map per face, we have to sum up the squares of the three conditions I had before, and we of course sum up over all faces. For conformal mapping, it is analogous. We can easily incorporate things like proximity to a reference surface, and this is used later on quite a bit. This is why I mention it. If you want certain vertex VI stay close to some reference surface, we do the following. In each iteration, we first compute the closest point to VI, so to the current position of VI, which is called here VI star, and takes the tangent planes there, takes the normal, which should actually be almost the same as this here, right? Actually, exactly. And then in the next iteration, we make sure that VI, or this is VI, is close to this tangent plane. So we express a proximity to a reference surface by proximity to the tangent plane at the closest point at the previous iteration. And this works very well, and there are arguments why this is good, simply because the second order Taylor expansion of the squared distance function of a surface evaluated at the surface is the tangent plane. So I see many papers which try to keep points close to these closest points, and this is a very bad idea if it is necessary that the mesh vertices glide over the surface. And even more important is the following: we have to impose some fairness constraints in our optimization. This comes in with some weight that initially is not very small, but during the iteration gets smaller and smaller. And this fairness here expressed on those polylines which should approximate smooth curves just with help of a sum of squared second differences, right? So VI, Vj, Vk here are consecutive vertices in a mesh which should lie on a smooth curve. We add this as a fairness term. Towards the end of the iteration, we can set this to 0, but initially it is important, and it makes sure that the differences we are using can actually be interpreted as derivatives. This avoids an unsmooth surface, but even it also avoids the following effect which could happen. Think on the left-hand side here on this checkerboard pattern from congruent squares. You could actually get some auxetic behavior of it. You could map it even into this case where the white faces totally disappear, which is of course not an isometric map. It is some auxetic behavior which can be exploited and which we do in another project, but not when we model an isometric deformation. And this behavior is also automatically prevented if we apply fairness to the control mesh. Here is a simple example. We take an initial quad mesh and optimize it so that the faces have associated parallelograms, which are actually squares here. So we get the checkerboard pattern from black squares, means each quad in this mesh has orthogonal diagonals of equal length. This is a conformally parameterized surface, and we can even keep here the reference surface. It also works here for the bunny, which is a closed surface. So if we have an initial quad mesh, which would be associated with a checkerboard pattern from parallelograms, but we can optimize towards squares, which would give again a conformal parameterization. And this is possible due to the Riemann mapping theorem and due to the fact that for this topology and sphere topology, we have only one conformal class. This is no longer true if we take, for example, a double torus like here on the left-hand side. The quad mesh, the control mesh is not shown, but what is shown is the associated checkerboard pattern from parallelograms. And when we here try to optimize for squares, we will see a shape change, because here in this for this topology we have not only one conformal class, but infinitely many. Another example is here on the left-hand side. You see some surface mapped into the plane, with a conformal map that is as isometric as possible. This is very easy in our setting because we can take the scaling factors lambda close to 1 in our optimization. What you see here, these squares are not the squares I was talking about. This is just some texture. The corresponding control mesh is here, the blue mesh is here mapped into 2D, and then in 2D this is this kind of texture with red and black squares mapped back, and you see it looks really like squares here on the surface, confirming that this is a conformal map. Another example is this. We have some deformation of this can, initially not isometric, but then if we make it isometric, it must of course be a piecewise developable surface, and we have these features here, these creases, which come up also when you take a can and you try to bend it. Another example is here. We have a rotational surface. We cut it open along a profile curve and isometrically deform it. Please note that if we have a rotational surface, we can, let's say, segment it into, decompose it into panels, and along these rotational circles, we have congruent panels, right? This is by rotational symmetry. Here they are hexagonal panels, not so important. And when we isometrically deform them, all these red panels here on the rotational surface are congruent. And here on the isometrically deformed, they are isometrically equivalent, which means in an application where we work with material that can be bent, still after production, like sheet metal, we can produce these panels with a relatively small number of molds corresponding to this pattern here on the rotational surface. So roughly speaking, we can produce n squared panels with n molds. Even more special, if we take the example from before and make our design from surfaces of constant Gaussian curvature, then a single mold is necessary, namely a mold, which represents a part of this sphere so that we can produce these panels. And then after production with the mold, we still can bend it a little bit on site in order to bring them to place, and we would get here completely smooth surface. So now I go to an important special case, namely the case of discrete developable surfaces. So let me recall, a developable surface pops up when we take some originally flat material which bends but doesn't a certain fabric. And so a developable surface is by definition a surface which is isometric to a part of the plane. Also is true for sheet metal, which we see exploited in Frank Gehry's architecture, to some extent also true for certain types of wood. For the following, I need the concept of a Gauss map, which uses a smooth surface for now, and at a point we have then a unit surface normal, and we view this unit surface normal as coordinate vector of a point. Of course, this is a point on the unit sphere centered in the origin. And this is the so-called Gauss map from the surface to the unit sphere. And for a developable surface, the Gaussian curvature is 0, which implies that the Gauss image is just a curve and not some domain on the sphere which has an area. So for example, here we have this cylinder, a vertical cylinder, then all the normals are horizontal, if you like, and therefore the Gauss image is this horizontal great circle. Form a ruled surface, but a developable ruled surface, and again the tangent plane touches along the entire ruling. An old and well-known discrete model of a developable surface is given by a strip of planar, let's say quadrilaterals, like here. So we have these planar quads, and of course we can isometrically map it into the plane by just applying appropriate rotation about these edges where the quads are joined to make the entire thing flat. Now, if we take such a quad here, it is planar, so these opposite edges must intersect here at the point, or in limit case be parallel. So we get such a polyline of these intersection points, where now these edges, where as these quads, neighboring quads join, are actually the connections of consecutive points. So we could actually see here this as a discrete version of a tangent surface, this being the curve which we use to define the tangent surface, and the connection of consecutive vertices, these edge lines or discrete tangents, form the discrete rulings, if you like, of this discrete developable surface. And you also see it can of course happen that all these points are the same, which is a discrete cone, or these points are, this point is at infinity. In other words, all these lines are parallel, and then we do have a cylinder. So we see also from this discrete model immediately the three different types of developable surfaces. With such a discrete model, we can apply some refinement rule, but a linear refinement rule is not enough. We always have to make sure that we keep the planarity of faces, but if we do so, we will in the limit get a developable surface. And this is shown here in this example, starting from this strip of planar quadrilaterals. We refine in this case by cubic lane Riesenfeld subdivision, but we also, after each step, make sure that the quads stay planar. So it's a kind of nonlinear subdivision method, which generates something like which looks like a free-form surface, a B-spline surface, but it isn't. But a little bit later, I will talk about how to get B-spline surface at least very close to developable. Another thing which we see already at the discrete model, but of course at the smooth continuous surfaces as well, is the case where we investigate this so-called regression curve, whose tangent surface is a developable surface. And this regression curve is called regression curve because actually when you take a plane and cut the surface with it, these intersections have a cusp there. So it turns back in itself. So it's a singular curve. And for applications, for most applications, it has to be avoided, which is also the inherent trouble in this dual viewpoint of developable surfaces, because one could actually access them without any constraint by viewing them as envelopes of one parameter families of planes. But then one has a hard time to rule out, to eliminate the regression curve from the areas of interest. So now I'm coming to a much more recent discrete model for developable surfaces coming from Olga Sorkin-Hornung's group. And I think Olga is around today. And they observe, of course, at first a well-known phenomenon. If you isometrically deform a developable surface, the ruling pattern may change significantly. So here you see on the left-hand side the developable sheet, which is has a planar part and 4 cylindrical parts. And you can easily deform it into such a conical sheet, which has a totally different ruling pattern, simply because these rulings are not preserved under isometries, and which is a big disadvantage of ruling-based methods. And Rabinovich et al., they discretize now a developable surface by the existence of an orthogonal net of geodesics. It is relatively easy to show that a developable surface is characterized by the existence of orthogonal nets of geodesics only. In one direction, if you have a developable surface, it's trivial because you can unfold into the plane and put rectangular grids there and map back. In the other direction, it follows, for example, immediately from the Gauss-Bonnet theorem. And there's a very nice discretization for this discrete orthogonal geodesic nets, namely quad meshes where in each vertex the 4 angles here are the same. So this angle alpha is not constant over the entire mesh, but per vertex we have 4 equal angles. And you see immediately certain nice properties from this discretization. There are no rulings in the formulation, but afterwards, if you have computed such shapes, you can fit rulings to it. And it is, I think, obvious how we will handle developable surface in our setting. We will consider a quad mesh M a discrete developable surface if it is isometric to a planar quad mesh M prime. In this image here, this planar mesh is an orthogonal, a rectangular grid, but this needs not be. And we will see a lot of examples where it's an advantage that it is not a rectangular grid. At first, we have a rectangular grid, let's say a square grid in the plane. So we get our discrete developable surface, if you like, in form of a checkerboard pattern. This is what our isometric model will make out of it. If we do it without fairness, the optimization, it looks a bit crumpled, which may also be seen as a developable surface, but clearly not the discretization of a smooth one, but with fairness, it is pretty good. This is the case which is very closely related to Rabinovich et al. Here's even a physical model of this checkerboard pattern from black squares. And so it is having here the spherical joints. And now I show a video which unfortunately also has some kind of audio behind. And you see how this nicely can glide along the developable surface, which is here done by the metal. And this confirms somehow by physical model that we are not wrong with this discrete model. Now you can control the quality by looking at the Gauss image. The Gauss image here may simply be formed by the normals of these parallelograms in the checkerboard pattern, and it turns out to be really curve-like, like here. Or you can also fit rulings. You could even come up with a kind of estimation of points on this regression curve. So here is a simple example. We take on the left-hand side a discrete developable surface according to our model. Here the isometric unfolding is a square grid. And then in 3D, we perform an affine map. An affine map is, of course, not an isometric map, but it maps a developable surface onto a developable surface, simply because the rulings, the straight lines, are mapped to straight lines, and the constant tangent plane along them is also mapped along to a constant tangent plane along the images of the rulings. So developability is preserved, but the unfolding is very different. And with our representation, we will have a corresponding isometric map mesh in the plane, which is of course no longer a square grid. Now let's briefly address the developable B-spline surfaces. I have only this slide on it. So with a B-spline surface has a control mesh, like here's this blue quad mesh. And we consider here, let's say a cubic, bicubic B-spline. And then we can think of performing subdivision, let's say Lane-Riesenfeld subdivision, let's say twice or 3 times. Then we get the refined mesh, which is this black mesh here, this finer mesh. And in order to have a developable B-spline surface, which is very close to a developable surface, we make sure that this refined mesh is discretely developable, which means that it is isometric to a mesh in the plane. This is this mesh here in the plane. So this is an optimization where the variables are not vertices, these red vertices here of the coarse control mesh, and the optimization ensures that the refined mesh, let's say after 2 or 3 steps of subdivision, is isometric to a planar mesh, and then you can confirm this is as developable as is necessary for most application. That would not be possible with the discrete model of Rabinovich et al., because it can be shown that a surface which, a B-spline surface, which possesses an orthogonal family of geodesics as isoparameter lines, that this is actually a cylinder. So here is a result. I think it could be used to fill a gap in current CAD/CAM software, which still is relatively weak when it comes to the modeling of developable surfaces. And it's not ruling based. If it's ruling based, it's much easier, but if it's not ruling based, I think this is a valid approach. We can do many other things, like, for example, we take here 2 planar sheets. They have this actually convex here and have the same perimeter, boundary curve length. And then we can, let's say, move one point to a point on the other and start gluing them together. What you get is a so-called D-form, and the virtual model and the physical model very nicely agree here. It's a bit more difficult if the sheets are not convex anymore. Then this is not such a smooth surface, which is verified both by the paper model and by our digital model. Here are a few more examples, and you always see a relatively nice correspondence between the physical model made from paper and our digital model. And this gluing is very simple because we can take here a quad mesh where the boundaries which should be glued to be together are edges in this mesh. Here's another example of this type. We have here a planar sheet. We cut 3 holes, and we would like to close the holes, which will of course fold up the surface into some developable shape. And here is an animation of what happens. And this is actually not difficult at all to model with our approach. It would be very hard and actually impossible, I think, with a ruling-based method. Or we could do curved folds. Again, here the curved fold is included in the mesh, the fold curve, I should say. The interesting case here is that these creases which arise when we fold up here fade away into a smooth surface, which is something that hasn't been considered so much previously. And again, we can verify it with a physical model. Here is an isometric deformation of a surface formed by developable panels. So if we have a valid panelization here by isometric deformation, we get again valid panelizations, valid, I mean, with developable panels. Now let us compare with the method by Rabinovich et al., and we do a very simple comparison here. We take a developable surface through a boundary and try to do this with the surface which looks very close to developable. To me, it looks like a piece of fabric, right? But it's not really a developable surface simply because of this restriction to a square grid in the parameter domain. And of course, with our method, it's more easy because we do not have this restriction. Maybe a more important comparison is the following. It's a method by Stein et al., which was published at SIGGRAPH 2018. They take a triangle mesh and turn it into a piecewise developable surface as follows. They try to make sure that at each vertex of the triangle mesh, this vertex star is a hinge. A hinge is a vertex star whose faces, whose triangles lie in 2 planes. So these are here in 2 planes. The intersection line of the 2 planes is here, and is of course a discrete ruling. A disadvantage is that what comes out here depends on the combinatorics of the original triangle mesh. So when we take here this surface under A and apply Stein's method for 2 different triangulations, we get 2 different solutions. For a piecewise developable surface, which is not an approximation or a good approximation of a single smooth developable surface, which we can get very easily with our method shown here. And we do not even need an alignment of rulings at the boundary. So here, this is not the ruling actually, it's slightly curved. Now, applications in architecture. This is not precisely what I'm talking about. Mappings between surfaces, mapping between a plane and a surface, namely this special discrete parameterizations. And here I talk about things which involve the second order of differentiation. So the motivation comes from architecture, where freeform architecture, I have talked about this, I guess, too often already. It is an advantage if the panels are simple, and quadrilateral, flat quadrilateral panels are an advantage, which is seen, for example, in this more recent real project for a shopping mall in Melbourne. To planar quadrilateral panels. So we are interested in meshes from planar quads. But we are interested here in a case which is also very desirable, namely where these quads are nearly rectangular. Then it is known that the redirection of edges in such a mesh must follow roughly the principal curvature directions of a smooth underlying reference surface. So these meshes are also called principal meshes. And in discrete differential geometries, they are well studied and come in two specific types, namely so-called circular and conical meshes. I'm not going into any detail here, but I just mentioned it is not completely obvious to come up, let's say, with the definition of this conical or circular mesh when you look for panels that are nearly rectangular. However, when we look at the checkerboard pattern, it is completely obvious, as we will see in a moment. So at first, we would like to make sure that our checkerboard pattern does not only have planar dark faces like these parallelograms, but also these white faces are planar. In order to get the white faces planar, we observe that a white face in this pattern is always a scaled version of a face in the diagonal mesh, right? So the corresponding face in the diagonal mesh is twice as large as the face here, so in this white face. So we just have to make sure that all these faces in the two diagonal meshes are planar. That's not hard. And if in addition we want to have this orthogonality, we just make sure that the diagonals in each face are orthogonal. And we get then, for example, a checkerboard pattern which is formed by precise rectangles and by white faces which are planar and nearly rectangular. So for ideal smoothness somehow, it may even be better to use, instead of this checkerboard pattern, one of the two diagonal meshes which are also valid principal meshes. These diagonal meshes have another nice property. So I show you here such a checkerboard pattern from black rectangles and the associated diagonal meshes. Here are the diagonal meshes. I take a vertex of the red mesh. It lies inside a face of the blue mesh. And we can assign a normal to this vertex, namely orthogonal to the face of the blue mesh, which is planar. I've just said we want to have all these white faces to be planar, and therefore all the faces in the diagonal mesh are planar. So we have a natural definition of normals at the vertices, and we also have this nice property that the normals at connected vertices, connected by an edge in this diagonal mesh, lie in a plane, which is related to an application in architecture with help of so-called torsion-free nodes in a support structure. You take prismatic beams whose central planes lie in these connection planes, which I had mentioned here. Now, the planarity constraint itself is super easy. If we want the white face here around the vertex Vi to be planar, we take as an auxiliary variable the normal Ni, which we need later on anyway, and we just make sure that this Ni is orthogonal to the four edges of this diagonal mesh. Yeah, this is very obvious how to do this. We take the scalar products and this length of the normal we fix here to 1 in our optimization. We can also now easily say we are not only interested, let's say, in a planar quad mesh with a right angle, let's say with another constant angle. We just express this constant angle at the diagonals. It's super straightforward. Or we want to have these black faces to be rhombic, which means equal edge lengths, is also very easy. So I show you some examples. Here is a representation of a surface as a principal mesh, a checkerboard pattern from black rectangles. This is always possible, so any surface can be represented in this way, simply because we need to, this is a principal mesh, so it requires, of course, initialization by a mesh which follows principal curvature directions, which is well known how to do that. We can go for white planar quads and black squares. So sorry, here they are of course dark blue, but in the sense of a checkerboard, I speak about black. So these are squares here, also here. This represents a principal parametrization, which is also a conformal parametrization. And those surfaces are called isothermic surfaces in differential geometry. So we also have a very simple way of discretizing isothermic surfaces. Here's an architectural realization. Here's an example for a constant angle. So in these parallelograms, we have the constant angle 60 degree or of course 120 degree. Here's an example with a constant angle where all the black faces are rhombic. So this is actually a generalization of an isothermic surface where all the black faces would be squares to another angle. I'm not aware of any studies of such surfaces in differential geometry, but maybe they would actually be interesting. So finally, I'm coming to so-called asymptotic grid shales. And this is work originally done by Eike Schling, an architect in Munich who is now at the University of Hong Kong. He takes these straight strips of sheet metal, you see rectangular strips, much longer than wide, and he first arranges them here in 2D in terms of such a support structure, and then moves it up into 3D, and finally gets a structure like this. So here these curved elements in the support structure, of course, developable, and they are arranged orthogonally to some reference surface. And in this case here, which I show here, which is at the campus of the Technical University of Munich, we even have a constant right node angle. So what is the geometry of that? If we arrange a flexible straight strip just by bending and not stretching, so that it is attached orthogonally to a reference surface. So let's say here, this is this curve, and this lies on the reference surface. The reference surface itself is not visible here, but I'm sure you can imagine. But if this strip is attached orthogonally to a reference surface, so this curve has vanishing geodesic curvature with respect to the strip, because originally it was straight, this curve, before bending. But due to the fact that we have a right angle between the strip and the reference surface, the vanishing geodesic curvature of this curve with respect to this strip turns into a vanishing normal curvature with respect to this not really visualized reference surface. So the curve must be a curve which always goes in direction of vanishing normal curvature. So it is a so-called asymptotic curve. So this is only possible for a negatively curved surface. We know very well how to discretize asymptotic parametrizations of surfaces. This is done with so-called A nets. It's again a quadrilateral mesh where all the vertex stars are planar. A very simple constraint. And if in addition we have a right node angle, of course we would have a surface where the asymptotic directions are everywhere orthogonal, which would be a minimal surface. So this is the geometry behind. And we can easily get these asymptotic nets, these A nets, which have a kind of discrete orthogonality in the vertices or another constant angle with our approach. So we look at the diagonal meshes and we make sure that we get diagonal meshes which have planar vertex stars. So this is then a discrete asymptotic parametrization. We actually have two meshes then around, the two diagonal meshes, but the advantage is, yeah, expressing it is of course again with help of a normal. I think I can skip this. But the easy thing is of course the angle, right? In order to express a right angle, we just make the diagonals in each control mesh part orthogonal. So it's another way of designing discrete minimal surfaces. Here is a result, here as a grid shell. Another example, both in this checkerboard pattern approach and as a grid shell. Here with 60 degrees, so completely straightforward, just makes the diagonals equal to 60 degrees. We get a surface with a constant negative ratio of principal curvatures. Here as a grid shell. We can use these angles as a design parameter. So for the same combinatorics, different designs. Actually, such a design was already used in reality for the entrance of a hotel in Ingolstadt in Germany. This is the work by Eike Schling and Jonas Schikore. So our ongoing work goes into various directions. I just mentioned two. We are currently investigating paneling with isometrically deformable materials, so like sheet metal. And there it turns out that you can achieve quite a lot just with a few molds for panels which possess constant Gaussian curvature. So for me, it was surprising that you can get such nicely, almost smooth surfaces where all these patches have a constant Gaussian curvature. And of course, if this Gaussian curvature is positive, we just need a spherical mold. The color here indicates the different molds. For negative curvature, we need some surface of constant negative curvature, let's say part of a pseudosphere or other. And this is something, yeah, which we currently look at. Another thing is this auxetic behavior. One can actually use it to design something, namely what you get could be called a shape morphing mechanical metamaterial. So we start here with a part of a paraboloid, and by completely opening up, we get a very different shape. And with this, I would like to conclude. I think what was really, this is a project where we did this blue sky research with some people in management don't like at all. So you just do something which you're interested in and you have initially maybe no application. And then it turns out that it's actually quite useful. I hope I could show you it is useful as a discretization for differential geometric concepts and actually quite straightforward. First order is completely simple. Second order, I also showed some examples. I showed various applications, and most of them were examples which somehow combine computational design with aspects of fabrication function. I think this is also important, and of course nowadays done by many people in the field. And I guess that's all what I wanted to tell you. And I thank you very much for your attention. And I'm happy to answer questions. Thank you.
Thank you, Helmut. It was